Imagine pouring like millions of dollars of electricity into a supercomputer, tasking it to master advanced mathematics, and then realizing it's literally throwing more than half of its own homework straight into the trash.
Yeah, it is the invisible crisis happening right now in generative AI training.
Right, because there's this popular assumption you might have that making an AI model better at complex reasoning is just feeding it more data. Like, pouring a billion more textbooks into the machine until it magically gets smarter.
Exactly, but when you actually step into the architecture of how these models are trained to think, that assumption just shatters. We are looking at a training landscape that is hiding a massive, unsustainable waste of computational energy.
And welcome to the deep dive. Today, our mission is to unpack a state-of-the-art foundational research paper that tackles this exact bottleneck. We're exploring a brilliant, highly efficient fix for how large language models learn to reason.
Yeah, and the source we're looking at is a cutting-edge paper titled RLVR without ineffective samples, Group Prioritized Off-Policy Optimization for LLM Reasoning.
It's a mouthful, but let's start with the trap itself. To understand why the AI is wasting so much energy, we have to look at the current standard for teaching it, which is RLVR, or reinforcement learning with verifiable rewards.
Right. So RLVR is essentially the engine behind the massive leaps we've seen in AI coding and math capabilities.
Because you want the model to actually think, not just predict the next word.
Precisely. When you want a language model to solve a complex logical problem, standard pre-training isn't enough. So you give the model a prompt, and you require it to generate a chain of thought.
Like, it has to explicitly map out its logic step by step before it even gives a final answer.
Exactly. And because it's a domain like math or code, that final answer is objectively verifiable.
The compiler either runs or it doesn't.
Right. The math equation balances or it doesn't. So if the final answer at the end of that complex chain is correct, the model gets a reward of 1. If it's incorrect, it gets a 0.
It's a very clean, objective learning signal.
It is. But the learning doesn't happen from just a single attempt. For any given prompt, the model generates a whole batch of responses. Let's say 8 different reasoning paths.
Okay, 8 paths.
Yeah, and the algorithm evaluates this entire group, comparing the successful paths against the failed ones. By calculating the mathematical difference between what led to a 1 and what led to a 0, the model computes a gradient.
So it updates its internal weights to favor the successful logic.
Exactly. It figures out what worked and adjusts.
Which, that makes sense in theory, assuming the batch actually contains a mix of successes and failures. But the paper points out this fatal flaw called the zero-variance trap, right?
Yeah, they also call it ineffective samples.
Right, so if the model generates 8 responses and the math problem is just impossibly difficult, all 8 chains of thought might end in the wrong answer.
Which means every single response gets a 0.
Yeah. And on the flip side, if the problem is way too easy, all 8 get a 1.
And this is exactly where the system breaks down. The core mechanism of policy gradient updates relies heavily on variance.
Meaning there has to be a difference in the scores?
Right. If every response in the group gets the exact same score, whether that's all 0s or all 1s, the mathematical variance within that group is exactly 0.
Wow.
There's no baseline to compare against. There's no differential signal to tell the model why a specific token was better or worse than another.
So the mathematical gradient just zeroes out.
It completely zeroes out, and the model's weights do not update at all. It learns absolutely nothing.
It's like, imagine a chess grandmaster playing a million games against a toddler.
Oh, that's a great way to put it.
Right. The grandmaster is going to win every single game, getting a reward of 1 every time, but their ELO rating won't improve, their strategy won't get deeper, because the variance in the gameplay is 0. There's no friction.
Yeah. And conversely, if a toddler plays a grandmaster a million times, they lose every game. The score is always 0.
They don't learn the Sicilian defense, they just get crushed.
Exactly. So the sheer volume of games, or in the AI's case, the sheer volume of generated tokens, is completely irrelevant if the variance isn't there.
So if the AI isn't learning from these extreme cases, how much of our computational power is just, spinning its wheels?
Well, the source data reveals it's incredibly severe. During standard RLVR training, the ratio of effective samples consistently hovers below 50%.
Less than half.
Less than half. This means that for more than half of the training time, your supercomputer is grinding through these incredibly long, computationally heavy reasoning chains, only to throw the entire batch in the garbage.
Millions of compute cycles just evaporating.
Evaporating without shifting the model's intelligence a single millimeter. It's a massive waste.
So if this is such an obvious waste of cash and time, researchers must have tried to build workarounds, right? Like, how has the industry historically dealt with this zero variance trap?
Well, the field is basically split into 3 different theoretical approaches to solve it, but each of them hits a pretty hard wall.
Okay, what's the first one?
The most prominent is active sampling, and the state-of-the-art method there is called DAP. The philosophy behind DPO is essentially brute force quality control.
Brute force how?
It forces the AI to execute extensive rollouts. So instead of just generating the 8 responses it needs for a batch, it might generate 3 or 4 times that amount across a ton of candidate batches.
Oh, wow.
Yeah, and it tests them all in real time, deliberately hunting for the batches that naturally exhibit variance. Then it throws the zero-variance batches away and only forwards the effective ones to the actual fine-tuning process.
That it sounds like buying an entire grocery store just to find 3 ripe avocados.
That is exactly what it's like.
Like a high-frequency trading algorithm running a billion simulations just to find 3 profitable trades and deleting the rest. Sure, the trades are flawless, but the compute cost of the billion simulations negates the profit.
It's an incredibly steep trade-off. With DPO, the computational overhead of generating all those extra rollouts often exceeds the cost of the actual policy optimization itself.
There has to be a less wasteful way to get the good data.
Well, people thought so, which leads to the second approach, predictive sampling, using frameworks like MoPPS.
So instead of brute forcing it, they try to guess.
Exactly. Can't we just look at the prompts before we run them and guess which math questions will hit that sweet spot of partial success? This method uses Bayesian inference to estimate the success probability based on historical data.
Okay, so it tries to curate a medium difficulty curriculum.
Right, but there's a huge flaw there. The model's capabilities are non-stationary.
Meaning the AI is constantly getting smarter.
Yes, the AI's internal weights are updating after every successful batch. So a calculus problem that was impossibly hard at iteration 100 might be trivially easy by iteration 1000.
The target is constantly moving, so the predictions are just wrong.
They fall out of sync very quickly. And worse, by deliberately tailoring the curriculum to medium difficulty to guarantee variance, the framework inherently filters out the absolute hardest problems.
It accidentally excludes the exact boundary-pushing puzzles it needs to become state-of-the-art.
Precisely. Which leaves us with the third historical approach, known as trajectory replay.
Let me guess. If you fail a hard prompt right now and get all zeros, you dig into the archives, find a time the model accidentally got it right, and slide that old answer into the current batch.
You nailed it. Methods like ARPO do exactly that. They inject a previously successful trajectory into the current response group to force that variance.
But mathematically, doesn't that break the gradient? I mean, you're mixing an old response generated yesterday with a new response generated today.
It absolutely breaks it.
Because the model's weights shifted. It might have a 90% chance of making a logical step today, but the old model only had a 10% chance.
Yes, and if we connect this to the bigger picture, it creates systematic bias. Trajectory replay operates at the level of individual responses. Splicing a historical trajectory into a current batch corrupts the policy gradient estimator because the math assumes all trajectories came from the current policy.
So the learning updates become totally unstable.
Unstable, and if the current batch is suffering zero variance because all answers are already correct, adding another correct old answer does literally nothing.
Right. So we're looking at a massive efficiency dilemma here. You either get high-quality data at an insane compute cost, save money but get weaker AI reasoning, or poison your own math with old data.
Which brings us directly to the framework introduced in the paper, POPO, or Group Prioritized Off-Policy Optimization.
Okay, let's unpack POPO. How does it break this deadlock?
POPO's architecture is divided into 2 distinct components. The first deals with the data pipeline itself, which they call prioritized group replay.
Okay.
Remember how DPO threw out an ineffective batch and forced the AI to generate new ones from scratch? DPO eliminates that rollout overhead entirely. When it encounters a zero-variance batch, it simply reaches into a replay buffer, a first-in, first-out, or FIFO queue.
Right, a standard FIFO queue.
Yeah, and it swaps the entire useless batch with the historically effective one.
Wait, swapping the entire batch, not just placing one answer in, like, ARPO.
It's exactly wholesale replacement. Discard the current useless group and replace it with a complete previously generated group that is guaranteed to contain variance.
Here's where it gets really interesting. It's like a chef who completely ruins a dish. Instead of starting from scratch and chopping new vegetables, which is DAPO, the chef just grabs a perfectly prepped backup meal from the fridge that they made an hour ago.
That's a perfect analogy.
Yeah.
And to ensure the integrity of that backup meal, POPO enforces two strict criteria before anything goes into the FIFO buffer. The first is quality.
Meaning it actually has to be a good batch.
Right. POPO checks its reward variance. It only stores batches where the model was partially correct. If a batch was all zeros or all ones, it never goes in the buffer.
So that solves the variance issue entirely. You're caching complex subroutines that you know work. But what's the second criterion? Because even with a backup meal, it's still slightly older than what you're cooking right now.
Yes, and that's the off-policiness criterion. In reinforcement learning, using data from a past version of a model is called off-policy data. If the gap between the old model and the current model is too big, you get distribution shift.
The new AI just doesn't understand the old AI's logic.
All right. To prevent this, POPO strictly uses a recency-based replay strategy. Because the buffer is first in, first out, it only ever retrieves the most recently stored groups.
So it grabs the freshest backups possible.
Exactly. It ensures the behavioral policy that generated the data is as close as possible to the current policy.
But even with strict recency, there's still a gap, right? A batch generated 10 steps ago is still slightly off policy. If the AI blindly updates its weights using that, the math is going to destabilize.
It will, and that is the true breakthrough of this paper. This is the second component. Decoupled off-policy optimization.
Okay, this sounds heavy.
It's a bit dense, but to understand it, we need to look at how off-policy data is usually handled, which is a trick called importance sampling.
Which is where you calculate the ratio of probabilities, right?
Yeah.
Like how likely a step was under the new policy divided by how likely it was under the old one.
Yes, but when you apply importance sampling inside modern algorithms like PPO, proximal policy optimization, you run into a massive structural conflict. PPO relies heavily on what are called trust region constraints.
Let's clarify that for the listener. The trust region constraint acts like a tether for a rock climber. When the model wants to update its weights, the tether caps how far those weights can mathematically shift in a single update.
Right. It stops the model from taking a wild, erratic leap based on one batch of data and forgetting everything it already learned.
It keeps the learning stable.
Exactly. But here is the critical flaw in older methods. They tie the importance sampling ratio directly into that tether. So if you feed older off-policy data in, the trust region constraint activates and forces the new, smarter model to anchor its updates to the behavior of the older, dumber model.
The paper calls this a suboptimal constraint, right?
Yeah.
So what does this all mean? Are we basically putting heavy mathematical weights around the model's ankles? It wants to optimize forward based on the old data, but the tether says, no, you have to mimic the model from 10 steps ago.
Precisely. You're forcing it to regress. POPO solves this by introducing decoupled importance sampling. It mathematically severs the connection between the behavioral advantage and the trust region constraint.
So it decouples the optimization.
Exactly. It uses the off-policy data to figure out which tokens were good and bad, but when it applies the tether to keep the update stable, POPO anchors that tether strictly to the model's current immediate past step, not the distant behavioral policy.
Okay, so it translates the old AI's homework so the new AI can safely read it, without getting confused by the old AI's bad habits.
It extracts the variance without inheriting the outdated behavior. It's an incredibly elegant synthesis. You have a pipeline full of 100% effective data with zero extra rollout compute and a mathematical engine that perfectly digests it.
The theory is beautiful, but I mean, how did it actually perform when put to the test? Theory often shatters when it hits actual benchmarks.
Well, the researchers deliberately targeted the most notoriously difficult domains available. They evaluated POPO using the Deep Scalar 40K dataset.
And that's AME-level competition mathematics, right?
Yes. Problems where the required chain of thought can stretch for thousands of tokens. The search space for correct logic is massive.
Did they test domains outside of just pure math?
They did. They utilized the countdown number game, which requires complex numerical planning and combinatorial search. And they tested it on the Geometry 3K dataset, which forces the model to map visual geometric diagrams to abstract symbolic theorems.
Datasets where the zero-variance trap is historically just brutal. And what models did they use?
They implemented POPO on state-of-the-art architectures. Specifically, DeepSeek R1 Distill Quinn, both the 1.5 billion and 7 billion parameter versions, as well as the Quinn 2.5 base models.
Okay, so highly diverse, complex domains on deeply capable modern models. What happens when RPO goes head-to-head against DPO, the brute force standard?
This is the aha moment of the research. Across the board, POPO perfectly matched the high-resource, state-of-the-art DPO method in final test accuracy. The models reached the exact same level of elite reasoning.
Wow.
But PO achieved this while consuming only 30% of the rollout budget, resulting in roughly half the total runtime.
Wait, really? Getting the exact same A+ grade but doing 70% less homework? That is massive.
It is.
If you free up 70% of your compute budget during generation, you're not just saving money. You can take that budget and train the model 3 times as long. It completely shifts the ceiling.
It does. And there's another fascinating detail that expands that ceiling even further. POPO is orthogonal to predictive sampling methods like MoPPS.
Orthogonal meaning you can combine them? They don't interfere?
Yes, they are highly synergistic. When they combined MoPPS with POPO, MoPPS acted as the first line of defense, predicting the best prompts. But when the predictions inevitably failed due to the moving target problem,
POPO's buffer system instantly caught the failure and swapped in an effective group.
exactly. This yielded an even higher ratio of effective groups and a drastically faster policy improvement curve.
It's a compounding effect. So, to recap for you listening, teaching AI to reason is plagued by ineffective samples that waste time and money.
Because of the zero-variance trap.
Right. But POPO solves this by recycling recently successful reasoning groups and using decoupled math to keep the learning stable, achieving top-tier results at a fraction of the cost.
Which fundamentally democratizes AI development. Faster, cheaper AI training means making high-level reasoning models more accessible to researchers who don't have multi-million-dollar computing budgets.
It's shifting from trying to brute force AI with endless capital to actually engineering a mathematical architecture that learns efficiently.
But this raises an important question for the future of AI architecture. If we can now mathematically decouple an AI's past behavior from its current learning to squeeze out maximum efficiency, what happens when we apply these recency replay memory tricks to how AI interacts with human users in real time?
Oh, interesting. Like applying the FIFO buffer to a live conversation.
Yes. Could an AI effectively replay its past conversations with you to instantly optimize how it solves your unique problems today?
Decoupling that past context from its global weights to adapt to your workflow without explicitly retraining it.
Exactly. If it works for mastering abstract geometry, the potential for building deeply personalized, highly adaptive AI agents is an incredibly profound frontier.
A system seamlessly editing its own logic on the fly. That is definitely something to mull over. Thanks for joining us on this deep dive. We will see you next time.